Two clocks built identically, placed in different locations on Earth, and within hours they no longer agree, not because one is broken, but because time itself is running at different speeds. General relativity describes gravity not as a force pulling objects together, but as a geometric property of space-time. Mass curves the fabric of space-time around it, and objects follow the natural paths carved by that curvature. The more concentrated the mass, the deeper the curvature. The deeper the curvature, the more dramatically space-time bends in that region. One of the consequences of this geometry is that time does not flow at a uniform rate across space. A clock sitting deeper inside a gravitational field, closer to a massive object, runs measurably slower than a clock farther away. This is not a mechanical effect. The clocks are not malfunctioning. Time itself is progressing at different rates depending on where in the gravitational field the measurement is taken. Under general relativity, this is not a paradox. It is an expected feature of how mass shapes the metric of space-time. The predictions of general relativity have been tested with extraordinary precision. GPS satellites carry atomic clocks, and those clocks must be continuously corrected for time dilation. Both the slowing caused by Earth's gravitational field and the speeding caused by the satellite's distance from Earth's surface. Without these corrections, GPS positioning would drift by kilometers within hours. The corrections work. The system functions. On that basis, the theory appears confirmed. But confirmation at moderate gravitational fields is not the same as confirmation at extremes. When physicists apply the mathematics of general relativity to regions of extreme curvature near the event horizons of black holes, in the conditions of the early universe, at the boundary of a singularity, the metric warping that produces clock rate divergence does not approach a limit. It approaches infinity. The equations do not slow down and stabilize. They produce values that have no physical interpretation. Time is not simply moving differently across extreme gravity. The mathematical structure describing how it moves breaks down entirely. The observable pattern is not in dispute. Precision measurements confirm time dilation at every scale we can reach. Atomic clocks aboard aircraft, on satellites, at different altitudes on Earth's surface, all show the effect. The divergence is real, measurable, and consistent with the model's predictions within accessible gravitational regimes. The anomaly is not in the measurement. It is in what the measurement implies when extrapolated to the regimes the universe actually contains. Time moves differently across extreme gravity, and at the extremes the universe produces, the model describing that difference no longer produces coherent answers. The first candidate explanation is that the breakdown is not physical, it is mathematical. Under this view, the infinities that appear in the equations near singularities are artifacts of the coordinate system being used, not genuine features of space-time. Just as the surface of a sphere produces a coordinate singularity at the poles without any actual physical anomaly, the singularities in general relativity may reflect a limitation of the mathematical language rather than a real collapse of physical law. This interpretation has serious support. Physicists have developed alternative coordinate systems, Kruskal-Sakaris coordinates, Eddington-Finkelstein coordinates, that remove certain singularities from the equations. In these frameworks, the event horizon of a black hole is no longer a mathematical catastrophe. An object falling through it encounters no infinite values. The curvature at the horizon becomes large but not undefined. The coordinate artifact explanation holds in those cases. The horizon itself is not where the model breaks. The equations remain manageable there, depending on how the geometry is described. But the central singularity does not yield to this treatment. No coordinate transformation removes the divergence at the point of infinite density. Every mathematical framework applied to the interior of a black hole. Singularity produces the same result, values that cannot be interpreted as physical quantities. The clock rate divergence does not approach a very large number at the singularity. It approaches a number that the mathematics cannot express as a measurement of anything. The coordinate artifact explanation reaches its limit precisely at the point where the physical question becomes most urgent. The second explanation is that general relativity is an incomplete theory, accurate within a domain, but missing the physics that operates at extreme scales. Under this view, a more fundamental theory would replace the metric warping description of gravity with a framework valid at all curvatures, including the extreme regimes where the current model fails. The clock rate divergence observed in accessible conditions would remain a real feature of that deeper theory, but the infinities would not appear. They would be regularized, smoothed out by physics the current model does not contain. Quantum mechanics is the obvious candidate for what that missing physics might be. At subatomic scales, quantum effects dominate the behavior of matter and energy. General relativity does not incorporate quantum mechanics. The two frameworks have coexisted for a century as separate descriptions of nature operating at different scales. Quantum mechanics for the very small, general relativity for the very large. In most situations, the scales at which each applies do not overlap, so the conflict between them does not produce observable consequences. At a gravitational singularity, the scales converge. The curvature becomes extreme enough that quantum effects cannot be ignored, and the region is simultaneously governed by conditions that demand both frameworks. A complete theory would need to describe that convergence. Current physics does not have one. Every serious attempt to quantize gravity, to build a quantum theory of the gravitational field, has produced partial results. String theory, loop quantum gravity, and related approaches each handle certain aspects of the problem, but none has produced a complete, tested framework that reproduces general relativity at large scales while remaining well-behaved at extreme curvatures. The clock rate divergence at singularities remains unexplained by any of them, not because the anomaly is ignored, but because the frameworks needed to address it are not yet complete. This is not a gap at the edge of the problem, it is a gap at the center of it. The third line of inquiry focuses not on the mathematics or the missing theory, but on what happens to time operationally near a singularity. Under general relativity, time dilation increases without bound as an observer approaches infinite curvature. A distant observer watching an object fall toward a black hole, singularity, would see the falling object slow progressively, its clock appearing to run slower and slower relative to the observer's own clock. At the event horizon from the distant observer's frame, the falling object appears to freeze. Time from that external perspective effectively stops at the horizon. The object from its own frame experiences no such freezing. It crosses the horizon and continues inward. Two observers describing the same physical event produce irreconcilable accounts of what happens to time. Neither account is wrong within its own framework. Both are consistent with general relativity, but the two descriptions cannot be straightforwardly combined into a single coherent picture of what is physically occurring. This is not a semantic problem, it is a structural feature of the theory, a built-in asymmetry in how time behaves depending on the reference frame of observation. At extreme curvatures, that asymmetry does not resolve, it becomes more severe. No mechanism within general relativity closes the gap between these descriptions. The theory produces both accounts, endorses both as valid within their frames, and provides no further instruction for how to reconcile them. General relativity correctly predicts time dilation in every regime physics has been able to test. Predictions match measurements to more decimal places than most physical theories achieve anywhere. On that basis, the model is not wrong in the domain where it can be checked. What cannot be checked is the regime where the model predicts its own failure. No measurement can be made at or beyond a black hole's event horizon and returned to an observer. No instrument can be stationed at a singularity. The conditions under which metric warping produces infinite clock rate divergence are precisely the conditions that are observationally inaccessible. The breakdown of the model occurs in a region from which no data can escape. The contradiction with existing models is therefore not fully testable. It is inferred from the mathematics of a theory that is otherwise accurate. Applied to a domain, the theory explicitly cannot handle. Physicists do not disagree that the equations break down. The disagreement is over what the breakdown means, whether it reflects missing physics, a mathematical artifact, or something about the structure of time itself that current frameworks cannot represent. None of those positions has been confirmed. Each produces predictions. None of those predictions has been tested in the regime where they differ. The metric of space-time defines how distances and durations are measured at every point in the universe. Extreme concentrations of mass warp that metric. Where the warping becomes severe enough, the mathematical object describing how time progresses ceases to produce finite values. Physics currently has no framework that remains valid at that boundary. General relativity reaches it and stops. Quantum mechanics does not apply there in any form that has been verified. The proposed theories that might bridge the two have not produced testable predictions in that regime. The clock rate divergence observed in accessible gravitational fields is real, measured, and understood within the domain where measurement is possible. Where the divergence becomes infinite, the boundary of current physics is not a region of high uncertainty. It is the region where the concept of a clock rate may no longer apply at all.